A thermodynamic system may be required to reduce the pressure of a fluid without doing other useful effects. The pressure drop of a fluid can be made through a throttling process. A throttling device provides a resistance to the fluid flow. It causes a significant pressure drop in the fluid. The greater the flow resistance, the greater the pressure drop across the throttling device for a given mass flow rate. It may be constructed with a small hole in the pipe or adjustable valve, capillary tube, or porous plug. Throttling is widely used in engineering. Most valves are considered a throttling device. The throttling device can be found in refrigerations and air conditioning systems. It is used to reduce the pressure of the refrigerant by simply restricting the flow. A liquid refrigerant passes through a throttling device, the pressure is reduced, and the refrigerant evaporates at a low temperature through the throttling device. Throttling device can be analyzed under the steady operation conditions. It does not involve any work other than flow work of the flowing streams. The velocity of the fluid may be very high inside the throttling device due to the small cross-sectional area. But the change in velocity of the fluid between the upstream and the downstream of the device is small, so we can neglect the kinetic energy change. And typically the throttling process is considered an adiabatic process. So it assumes to have no heat transfer between the throttling device and the surroundings due to the small size of the device. So Q dot drops out. Under these assumptions, the equation is reduced to H1 equals H2. So the simplified equation states the enthalpy at the inlet is equal to the enthalpy at the outlet. So enthalpy remains constant across the throttling device. If an ideal gas undergoes a throttling process, the temperature remains constant, since H, enthalpy, is a function of temperature only. For real gases, the enthalpy is not a function of temperature alone. So the temperature before the throttling device and after the throttling device may not be the same. Example 4.9. A supply line carries a two-phase liquid vapor mixture of steam at 300 pound-force per inches squared. A small fraction of the flow in the line is diverted through a throttling calorimeter and exhausted to the atmosphere at 14.7 pounds per inches squared. The temperature of the exhaust steam is measured as 250 degrees Fahrenheit. Determine the quality of the steam in the supply line. So this is a throttling calorimeter that determines the quality of a liquid vapor mixture. So the device allows the liquid vapor mixture to expand and change the phase into superheated vapor. So in this diagram, it looks complicated, but this is throttling device. So this is position 1, position 2. At position 1, the phase of water is saturated liquid vapor mixture. At position 2, it's in superheated vapor phase. Assuming this is an adiabatic process, the potential energy, kinetic energies are negligible. There is no work involved in the process. So we can simply say that H1 equals H2 across the throttling device. At location 2, pressure and temperatures are known, so we can determine H2. So at location 2, pressure 14.7 psi, temperature 250 degree Fahrenheit, enthalpy H2 is here. H2 H1 can be expressed in terms of the quality. So we know the pressure at location 1 at 300 psi, enthalpy for saturated liquid, enthalpy for saturated vapor. So quality before the throttling device was found. So in this problem, the throttling device caused the pressure to drop 300 psi to 14.7 psi. It dropped by a factor of about 20. And the temperature dropped from 417.4 degree Fahrenheit to 250 degree Fahrenheit. It's about 167 degree Fahrenheit.